my master's. I pursued my master's in I came in 2017 to UH and I started pursuing my master's under Dr. Joyner. Then I graduated in 2019 and in 2020 I started working under Dr. Ray for my PhD. And I primarily worked in radiation effects on semiconductor memories. So here's some of my work experience. I worked as the GTA for a couple of years, and then I've been a GRA since. I've also done my internship last summer as a media architecture engineering intern in Micron. Some of my awards, my colleague and I, Will, he's right here. So he and I received this Best Poster Award in IEEE Paint 2022. I was awarded a GRSP Alabama XCOR Fellowship last year. And this year, I've been awarded the Outstanding Graduate Student Award for Electrical and Computer Engineering. Dr. P's in that picture as well. So here's a list of my publications. The top 10 have been accepted. There's 5 first author and 5 co-author publications, and another 2 first author publications under review. A summary of which I'll be presenting in this presentation. So the outline is as follows. First, I'll go into motivation, why I started my research in this field, what the motivation for research in this field in general is. Then go into some of the background. Then we go into SRAM radiation effects first, and then some of what we saw in my qualifying exam for the radiation effects on NAND flash, and then the presentation. So primary motivation is after I finished my master's in 2019, I came across this TV show from HBO. It's called Chernobyl. And that basically was about the nuclear disaster in Chernobyl, reactor 4 exploding, and then how people had to clean it up for damage control, basically. And what stood out is one of the episodes had showed how they tried to use robots, and after deploying the robots, they work for a couple of minutes and then they die. So they had tried that with multiple robots, they all kept dying, so basically they had to send people as dubbed as bio-robots, and people were who cleaned up, and that put them in substantial health risk, right? So it's being exposed to radiation. So that didn't sit well with me. I used to have nightmares. Basically, I wanted to understand why semiconductor devices are affected by radiation, and that's how my pursuit began. Luckily, there's Professor Dr. Ray, and he was working exactly on that field. He was working on radiation effects on semiconductors, and so I took up his class, and the rest, as he mentioned, is exactly what happened. But the commercial motivation for this field of research is, in the recent years, as you can see in this chart on the right side, the number of satellites have exploded. So that's basically an exponential growth. And these satellites, to keep the cost down, they usually use commercial off-the-shelf electronic components. So these are not radiation hardened, they're just commercial components. So it's important for us to understand how radiation affects these components. So unlike on the Earth's surface, where we have the Earth's atmosphere, the Earth's magnetic field to protect us from all sorts of bad radiation from outer space. These satellites, which are very close to the edge of the space and also deep space probes, they have no protection and radiation affects them a lot. And so future will rely increasingly on commercial parts, so it's important for us to understand the radiation effects in them. So here's a few different sources of ionizing radiation. We can classify them into 2 main branches. One is particle-based and one is photon-based. So high-energy particles can be of several different types, primarily heavy ions, which are really large nuclei which have been ionized, and they are traveling at the speed of close to the speed of light, I'd say. And they essentially arise from exploding stars, and they can be very dangerous to electronic components. They cause what's known as single event effects. There's other things like protons and neutrons and electrons. Protons and electrons are the biggest contributing sources in the Van Allen belt. They cause TID. And there's photons like X-rays and gamma rays, which have incredible penetration because, well, they have no mass. They interact very little. And so they penetrate a lot. There's a picture showing the depth of penetration for different things. Alpha can barely penetrate a piece of paper. Beta penetrates maybe your hand. Neutrons are stopped by water, and gamma just penetrates pretty much everything unless there's like a thick substance of lead which can stop it. So most of my research is on total dose. So the dose selection is pretty important. The way we decide that is knowing what the possible dose ranges are for different components deployed in different regions. So for example, the low Earth orbit satellites usually accrue about a few kilorads every year. The geosynchronous orbit, which is much higher up, they accrue about 100 kilorads in about 10 years, which is the normal lifespan of a satellite. There's also medium Earth orbit where the Van Allen belts are, that's pretty damaging because they can accrue up to 100 kilorads every year. So going to some of the basics of radiation effects on MOS devices. Picture on the left shows a MOSFET, and when you expose it to ionizing radiation, essentially that radiation is going to ionize the oxide layer. So what do I mean when I say ionize? When I say ionize, I mean it will cause a charge pair production. So it'll ionize the oxide and produce a positive and a negative charge. But the electrons are high in mobility, they'll quickly drift in the field of the direction of the electric field. And the positive charge, which are low mobility, they might get trapped either in the bulk of the oxide or they travel towards the interface of the oxide silicon and they trap there. Essentially, when you trap positive charge, the threshold voltage of the MOSFET decreases. So that's the gist of it. So there's an important metric, which is number of holes which are produced during ionization. So that's given here as a function of electric field times G naught, which is a constant, times dose, times the thickness of the oxide. So the dose and thickness of the oxide play an important role in how many holes you produce and how much the threshold voltage shift is going to be. So you've seen some of the backgrounds. Let's get into radiation effects on SRAM or static random access memory. So there's multiple different types of SRAM. So the one most commonly used is a 6-transistor version, which is shown on the picture on the left. Essentially, there's 2 NMOSs, 2 PMOSs, and 2 access transistors. So the 2 NMOS PMOS pair in the middle is basically 2 cross-coupled inverter pairs, and they can hold either a 0 or a 1 bit, essentially. So SRAM is really fast memory. So you use it in what is called cache memory for computation. That's usually what's inside CPUs and all the calculations is very important. But it's volatile memory, meaning when you turn off power, the data that's stored on the memory is lost. And the picture on the left shows how they've been scaling over the years. The cell size has been reducing rapidly and the total memory density has been increasing. So as for radiation effects on SRAM, they're most commonly affected by what's called single event effects. That's where a large heavy ion comes in contact with a sensitive node. It'll ionize and produce some pairs there, and it'll produce a current which is going to cause the state of the cell to flip. So that's not a good thing because when the state of the cell flips, that's an error, right? And we don't want errors. As far as TID goes, SRAM is pretty resilient to TID. Their general functionality is just fine, even up to several megarads. But there are other aspects of the SRAM which are affected by TID, some of which I'll be explaining in the following slides. So, okay, how does TID affect SRAM cells in specific? So we saw how TID affects MOSFETs. SRAM is made of 6 MOSFETs, right? So there's 2 PMOSs and 2 NMOSs which primarily hold the data. The threshold voltage of a PMOS, the magnitude of the threshold voltage increases, but for NMOSs, the threshold voltage decreases. So essentially, TID will cause PMOS will make PMOS more difficult to turn on and NMOS more easier to turn on. That's essentially what happens. Another factor, like we saw in that equation, is the electric field is very important. So if the MOSFET is turned off, the electric field is very small. And so the fraction of unrecombinant holes will be very small. But if the MOSFET is turned on, the TID effects will be much larger. That's important. I'll be explaining why in the following slides. So I mentioned that SRAM is volatile in nature. So when you store data, you turn off power, turn it back on. When you turn off power, the data is lost. But when you turn it back on, how will it turn on? Clearly, it will not contain the data that you wrote on there, but it will contain something. What is that? Will it power on as a 1 or a 0? So that is decided by certain inherent threshold voltage differences between these MOSFETs. Ideally, you design them to all have the same threshold voltage, but during manufacturing, certain MOSFETs can have more traps in the oxide. There can be geometric differences during fabrication. Things like that will cause the threshold voltage of these MOSFETs to be different. So what happens from that, I'll explain in the following slides. So let's assume that the transistor P1 has a smaller threshold voltage and P2 has a larger threshold voltage. What that means is when you apply VDD or when you turn on the circuit, P1, since it has a smaller threshold voltage, will drive a larger current, charging capacitance Cout1 to charge faster compared to Cout2. Cout2 will still start charging, but will be slower. So when Cout1 charges, it's going to turn on MOSFET N2. When MOSFET N2 turns on, the capacitor Cout, which was starting to charge, will now start to discharge again, which is what is indicated in that plot on the right-hand side. So Will and I worked on this paper together. He's right here. Anyway, so here you can see how Vout1 charges to VDD and Vout2 discharges to ground, essentially because P1 had a smaller threshold voltage than P2. Same can apply to N1 and N2. If that has a bigger difference, then that's what will be the deciding factor. What's worth mentioning is if P2 had a smaller threshold voltage, then this cell would have been a 0 as opposed to now being a 1. I've seen the basics. Let's get into understanding how this comes into play. So I mentioned how an SRAM cell turns on. So inherently, either turns on as a 1 or a 0, irrespective of what was written onto it before. Because it has this inherent signature, every SRAM circuit has this inherent signature. It's almost like a human fingerprint. So we can identify devices based off of that fingerprint. So let's consider two chips. Chip 1, when you turn it on, it's always going to have, well, I wouldn't say the same response, but a very similar response. There might be a small variation in response. And chip 2 will also have some response. But these two responses will not be equal because the signatures are unique to each device. They're very random in nature, and it's fairly reliable as far as the repeatability of these signatures. So it's easy to distinguish between two different devices having two different SRAM modules. So this metric is used to identify devices, right? So essentially device authentication. Another use can be this is not almost, it's definitely a true random number, right? Which can be used in cybersecurity for cryptography keys. So that's another use. And radiation affects the SRAM circuit's capability to produce the signature. We'll see how. But to see how, essentially, this is the setup that we use. So this device is composed of an Arduino Duo, which is a controller. And essentially that powers the socket, which houses that chip. These are commercial chips, automotive grade commercial chips. And essentially we can interface with these chips using this setup here. And the pin diagram is given on the left side. So, we carry out these experiments by exposing different samples to radiation, and that we mostly did at Ohio State University, some in San Diego National Labs as well, but predominantly in Ohio State University. So that's me standing next to the, well, behind me is a nuclear reactor, but the one that we are focusing on is that underwater cobalt-60 source. That's a 20 by 20 feet tank full of water, but at the bottom is some cobalt-60 pins that's emitting gamma rays. And at the dose rate is 11.5 kilorad silicon per hour. So some of the important metrics before we get into the results. So I mentioned the signature and how it can be different between devices, right? So to record the signature, you essentially get multiple readings, as in you take a reading, you turn off the SRAM circuit, turn it back on, take another reading, repeat that process. In this case specifically, we do that 101 times. And then we take a majority vote because, like I said, some of the positions, the bits flip back and forth. Majority will stay the same, but a few percent of bits flip back and forth. And so once we generate that gold puff, which is the reference puff for that chip, we compare all the corresponding authentication puffs recorded later to this gold puff. We see the number of bit positions that are varying, and we represent that as a percentage called Hamming distance percent. And the chart on the right is basically the baseline characterization of different samples that I've used for my experiments. The Hamming distance is anywhere between 2.5% to 6.5% before radiation. So some of the first results are we exposed 2 different samples from 2 different manufacturers up to 200 kilorads. And you can see how the Hamming distance percent goes from 2.5% to 25%. That's a huge change. So essentially what happens during authentication is we say, well, if the Hamming distance is about 5%, then it's an acceptable difference. You can authenticate that as a genuine device. But at 25%, that can be misconstrued as a different device. Because when you consider 2 different random signals, it's going to be what, 50% difference, right? So it's approaching that 50% difference pretty much. Cypress does a little better, but you still see a significant increase in Hamming distance. It goes to about 15% after 200 kilorads. So for authentication, you might be able to change the Hamming distance threshold, maybe instead of 10%, 15%, whatever, which is acceptable. But for cryptographic keys, you can't have any errors in there. So usually you have error correction circuits, but no error correction can correct. 25% fails, right? So that's pretty bad. So you have to figure out ways to mitigate this depletion of Hamming distance percent. So how do we combat the K effects on HRAM-puff? So there's multiple different ways you can tackle this problem. So one is from the perspective of technology nodes, that is the size of the transistor. Second is the type of data that it holds, meaning you can control the electric field in different MOSFETs. And the third is through annealing, that is removing it from the source of radiation and then just letting it rest. Each of these aspects we'll see in the following slides. So first, for technology nodes, we take 3 different samples. The first sample being 65 nanometers, 90 nanometers, and 150 nanometers. So you can see how the 150 nanometer Hamming distance increases by 8 log. It goes from 2.5% to about 11% after 100 kilorads. It's a very steep slope. But the 90 nanometer, the slope is significantly smaller. It's as if it's more resilient to radiation. And the black line, which is the 65 nanometers, from about 25 to 100 kilorads, it's basically a straight line, which is interesting. But there's a sharp increase from 0 to 25 kilorads. And the prediction is that the 65 nanometer cells are very prone to noise. They have a very shallow oxide. So depending on where the traps are, if it's because it's very thin, it's going to be very close to the oxide silicon interface. So that will cause a whole bunch of what we call random telegraph style of noise. So this noise predominates the increase in Hamming distance first, and then it almost flatlines because the number of traps saturate there. Basically, what the takeaway from the slide is that lower technology nodes usually are more resilient to radiation, and we will see why. So on the right side, there's 2 MOSFETs. One's a larger MOSFET, one's a smaller MOSFET. You can see how the thickness of the oxide is substantially smaller for the smaller MOSFET. And we know that the thickness of the oxide is a determining factor for total pole production for the DID effect. You can see how from this equation that's derived below, the change in threshold voltage is proportional to the square of the oxide thickness. That's why it makes a substantial difference for us to use smaller devices with thinner oxides because they're more resilient to DID. Okay, now from the aspect of stored data. So on the left side, there's the different data patterns that are possible, right? So with respect to the gold puff, we can either store the gold puff, or you can store the ones complement where every bit is the opposite of the gold puff. You can store all zeros, or you can store all ones. In each case, essentially, when you change the data that's stored, you're changing which of the 4 MOSFETs are turned on. For example, when you store a 1, you have P1 and N2 on. And when you store a 0, you have P2 and N1 on. And we know that by turning on, there's a stronger electric field in the oxide, so that's going to have a more damaging effect on the MOSFET. So there'll be a bigger change in threshold voltage. So by controlling that, we can control what the outcome is. So here's the interesting thing. On the left side, we're seeing a sample from the manufacturer Cypress. So the blue line, which indicates the effects of storing gold puff on the SRAM circuit, it shows how the gold puff locations perform significantly better than the inverted gold puff or the ones complement locations. So the Hamming distance depletes least in the one that's storing gold buff as opposed to the inverted gold buff. But on the chart on the right-hand side, which is from a different manufacturer, ISSI, we can see that storing the gold buff has the worst outcome, and storing the inverted gold buff actually causes a decrease in Hamming distance first. And then with dose, it almost comes back to the baseline. So clearly, there's a lot of difference in terms of the Hamming distance deterioration, depending on what data you're storing. Why? Here's why. So depending on, we discussed the threshold voltage mismatch, right? So depending on which of these MOSFETs are the determining factors in the power on, there can be two different effects. So the first effect is when the NMOS determine the power on. So if there's a bigger difference in the NMOS, here's what happens. When you store the gold buff data, you start off, let's say for example, the cell is in a zero state, right? So N1 is on and N2 is off, which means essentially your N1 had a smaller threshold voltage and N2 had a larger threshold voltage. So you keep the same pattern and expose it to ionizing radiation. We know that the MOSFET which has been turned on has a stronger electric field, so it will have a more significant change in threshold voltage. So threshold voltage of N1 will be even lower now after radiation compared to before radiation. So the power on state is kind of reinforced, as opposed to storing the reverse of the gold buff, which is if the cell is 0, you're storing a 1, in which case your N1 is off and N2 is on, your N2's threshold voltage will reduce even further, which means after radiation, your threshold voltage of N1 will be greater than threshold voltage of N2. So now you have kind of reversed the power on of that cell, which is why these data patterns have the effect that they do have. So the opposite case will be if the PMOSs are more dominant. And that's where storing the inverted buff data has a better outcome. And that's because, let's assume again, the cell is in a zero state. In the case of buff data, you will have transistors P1 and P2 being off and on respectively. Threshold voltage of P1 is higher than threshold voltage of P2. The magnitude of the threshold voltage is higher. Now, when you expose it to ionizing radiation, the threshold voltage shift for P1 will be more substantial. P2 will be more substantial, meaning your threshold voltage will increase further, and you have the roles reversed. You have threshold voltage of P1 less than P2. But in the case of writing your opposite data, that's the one's complement data, you're forcing transistor P1 to be on and P2 to be off. So P1 will have a more substantial change in threshold voltage, so it further reinforces what was before, which is threshold voltage of P1 greater than threshold voltage of P2. And after radiation the margin becomes even larger, so you're basically reinforcing the power on state of that cell. Here's more evidence. There's another manufacturer, Alliance, and samples being tested there. They show the same pattern as the ISSI, essentially storing the inverted gold buff pattern causes a decrease in Hamming distance, and that's the best outcome for Alliance as well. So we've seen how technology node and data pattern causes different effects. As far as room temperature annealing, or the process of annealing goes, essentially you're removing samples from ionizing radiation, and then you're just letting them rest. Specifically here, they're resting in room temperature with all pins grounded. So you can expect over time the positive charges which were trapped in the oxide slowly anneal, and when they detrap, basically when they detrap, the threshold voltage goes back to what it was before radiation, and so you can see the Hamming distance come back down after several months. It comes back down, but not quite to the same extent where it was before radiation, but it still does come back down. So that was on SRAM puffs, but there's still other metrics which get affected by TID as well, and we look into that. Now, again, I mentioned that SRAM is volatile in nature, right? But is there any way to make it non-volatile? Well, there is. So in this experiment, essentially, we are writing a certain data pattern. In this case, it's a picture of Dr. Albert Einstein. That's written onto a piece of memory that initially the puff looks like this. So it's basically zeros and ones, right? When you convert it to a picture, it's basically salt and pepper noise. This is what it looks like, and you're writing that image onto that location. And then you're exposing it to ionizing radiation. After 10 kilorads, 6.7% of the cells are converted towards the Einstein image. After 30, the image starts to emerge from that salt and pepper noise. And at 50 kilorabs, basically there's a perfect imprint of Albert Einstein. So essentially, even if you turn off the device and turn it back on, that gold puff has been now altered to this image permanently. Well, permanently is subjective, I guess, but long term, this image exists on that image location right now. Which is, of course, not what we expect for SRAM, right? Because it's supposed to be volatile. Now it's become non-volatile. So essentially, how this can be abused is you can steal data from SRAM locations by making them non-volatile. So when the device is turned on, there are certain security measures in place that prevents you from probing and reading out data. But when the device is off, those measures are well turned off, and so you can steal image from that non-volatile now SRAM. And for how long does this image stay written there? So this is immediately after exposure, but even after 7 days, you can still see parts of the image. And after 33 days, you can still see part of that image. After 50 days, you can still see parts of that image. So the percentage of match is reducing, but you can still see what was written on there. And what's left out of this slide is that after about 100 and something days, the image turns back to the perfect imprint of Albert Einstein, but that's things still we are exploring that, so that's excluded from the slide. Now, here's the summary of attempting the same experiments on different samples. We see something interesting. So, like we saw before, where the inverted data pattern can have a better effect for having distance. Here too, we can see both positive and negative imprints. So, negative imprint would be you write a 1, you burn in a 0 instead. So we see in certain samples like the ISSI and Alliance, the negative pattern is actually burnt in. But regardless of the negative or positive imprint, they both regress towards 0 when they are annealing. So that's interesting. There's another interesting attack vector. So this is called cold boot, and it's pretty common in both DRAM and SRAM circuits. Essentially, DRAM and SRAM are supposed to be volatile in nature, but when you reduce the temperature to sub-zero, basically make it very cold, the rate at which the data is lost slows down. So you can turn off, you can cool it down with, I don't know, various things like they use canned air, you invert it, you spray it on the memory, it cools down, or they can use cryogenic liquids, turn down the temperature, the data remains for longer even after the device is powered off, and then you can steal that data. That's been the attack vector. But this is also possible at room temperature, depending on how quickly you can pull out data. So the reason for these non-volatile memories taking some time to lose data is as follows. So this is the SRAM cell. Initially, it's in the cell state 1 when power is on, but when power is off, that is when VDD is grounded. Essentially, the charge or the node capacitance Q, which is basically an effect of the gate capacitance from P1 and N1, that node capacitance discharges through 3 different routes that I've marked with the arrows here. Can either discharge through the PMOS P1, A1, or NMOS N1. And it takes a certain amount of time for a certain charge to leak through these MOSFETs. That's where MOSFET subthreshold leakage comes into play. And you can derive an equation where it describes the amount of time it would take, depending on the capacitance, to have this data leak, essentially. So that's a strong function of threshold voltage. Basically, there's an exponential term there, and that threshold voltage plays a big role. So we know that radiation changes your threshold voltage. The threshold voltage decreases. So the amount of time taken to discharge will also decrease. And that is what before I go there. Firstly, this is the baseline characterization before exposing to radiation. You can see how gradually the data is lost as we increasing the amount of time the device is powered off for. So that's the baseline. What's interesting to see there is for the first 5 or so milliseconds, almost no data is lost, which is honestly enough time to state data if that's what you're planning on doing. But to further study this, we tried on different samples from different technology nodes. and the data loss curve for the different samples are as shown in this picture. You can see how the 250 takes the most amount of time and 90 takes the least amount of time. So we saw from this equation here, right, threshold voltage is an important factor. So as the size of the transistors reduce, the oxide thickness reduces, their threshold voltage also reduces. When there is a smaller threshold voltage, the leakage current increases, which is why the data is lost faster, essentially. And after radiation, it's decreasing even further. You can see how the black is in pre-radiation and the reds are post-radiation. How you can see they are shifting towards the left, as in the amount of time it takes to lose data decreases after radiation. Okay. So we have seen now the radiation effects on SRAM. I've already described some of the NAND flash TID effects for my qualifying exam, so I've kept it brief. So flash memory is the most common form of memory that we use. It's in pretty much every electronic device that we own. It has the highest data storage density, which is why it is very important. And for the same reason, it's also very useful in space. So it's important to study the radiation effects on NAND flash memory. So the top right picture shows a slightly modified MOSFET. Here you have, instead of one oxide, you have two oxides, and you have a layer which is storing charges. That's called the floating gate. Essentially, it's a modified MOSFET. And thanks to that floating gate, you can store some charge there, and that's what is storing data. Essentially, when you, okay, so the bottom right picture shows a threshold voltage distribution and two MOSFETs, right? So the first MOSFET has no charges on the floating gate. So that's an erased cell. So you program this floating gate by pulling charge into the floating gate. When you program the cell, the threshold voltage increases, so that distribution is moving up. So this is basically a single level cell or SLC flash memory. So taking it further, we have carried out experiments on MLC flash, where instead of storing 1 bit per cell, you store 2 bits per cell. So then you'll have 4 threshold voltage distributions, like the picture on the right-hand side. So because you have 2 bits per cell, each physical word line has 2 logical pages. So the lower page is called the LSB page, and the upper page is called the most significant bit, or MSB page. You can see on the left side, the red dots are the number of fails in MSB pages, and blue dots are the number of fails in LSB pages. So you can see 2 important things, right? Before I go there, the x-axis is different layers. So you can see a U-shaped pattern, first of all. So the edge layers are more prone to errors than the middle layers. And the next most important thing is the red dots are always at a higher position in the chart than the blue dots, meaning MSB pages are, in general, having more fails than the LSB pages. That's because you can see on the right-hand side, after radiation, the threshold voltage distributions shift. Those are the red curves. They widen and shift down. So the tail of these distributions goes into the reference voltage range. And so you have a whole bunch of errors. What you must pay attention to is the curve on C extends deeper into reference 3 than the curve on B, because C is at a higher threshold voltage. So again, the higher the threshold voltage, the stronger the electric field across the oxide, which means you'll be trapping more positive charges and also losing more electrons from the floating gate as an effect of TID. So a state C cell would suffer from a higher TID damage compared to a state B cell. Depending on the voltage, there'll be a certain ratio that happens. Here we're assuming 2 and 3 volts, so there's a 50% higher chance for C to B transition than B to A transitions. And that's what the results show. You can see always the MSB pages are more in error. So another aspect is, like I discussed, noise. So on the chart on the right side, on the left side, shows how I am not moving that pointer. I don't know how that's moving. Anyway, so the chart on the left has black bars, which are cells in the program state, and red bars, which are cells in the erased state. You can see how cells which are in the erased state always accrue more noise. After radiation, they have more noisy bits than the cells which are in the program state. And that's because of the direction of the electric field in the oxide for erased and programmed cells. So now the erased state cells, the direction of field will cause the positive traps to move towards the silicon oxide interface and trap near the interface. But in the case of a programmed cell, these trap charges towards the floating gate, it's in the opposite direction, right? So towards the floating gate and trap deeper into the oxide. So what happens is when the trap charges are closer to the oxide silicon interface, they have a bigger impact on the channel current because they can trap and detrap electrons from the channel current. So in the case of erased cell, because they're much closer to the interface, they're going to have a bigger impact as to how much they contribute towards noise. But in the case where the cell was in a program state, because the traps are much deeper in the oxide, they don't affect the channel current as much. So the cells will have lesser noise compared to the erased cell after radiation. So we've seen both radiation effects on SRAM and flash memory. So the final conclusions are as follows. So the SRAM puff we have seen deteriorates pretty rapidly with radiation, but we can change the degree to which the Hamming distance of the puff degrades with dose by controlling the data that's written onto it. And we can also turn SRAM memory, which is essentially supposed to be non-volatile, supposed to be volatile, into a non-volatile memory by storing certain data and exposing it to TID. And as for the NAND flash, we know that erased cells are going to have more noise after radiation. So generally the factory sells you the chips, all the blocks are in the erased state. But if you program it before deploying it in a radiation environment, that's going to help a lot, maybe up to 30% better. So it's better to pre-program these blocks. And that's as far as the NAND flash goes. So do you guys have any questions? I can take questions.
Good. Thank you, Umesh. Thank you for
our proceedings are here. It stays with the candidate, but audience opportunity to ask questions first.
So pre-programmed states that you're talking about, and as opposed to the zeroing out from the manufacturer, are you proposing that like you achieve or you receive something like that, you can program it yourself?
Yes.
Okay, and is there a pattern that it's a recommended pattern, or is it like you drive all ones, or how does that work?
No, so it depends, right? You have to understand that taking it to a very high program state also increases the feed across the oxide. So you wouldn't keep it in the highest program state, you'll keep it somewhere in the middle. Depends on what the gray code is for that memory. Depending on that, you can choose. Not the highest state, somewhere in the middle.
The question, so does the NAND flash have a similar behavior after radiation in the annealing process? Is that a similar?
Yes, that also anneals. So hold on, let me quickly show you some of the. Oh, well, I don't have the. But yes, that also anneals over time. Very similar to the SRAM.
Yeah.
Hi, Umesh.
Hello. Yes.
Yeah, so I have one question on the SRAM. So basically, can you go back to the Einstein page after radiation?
Yes.
Yes. So here, yes. So go to the next slide. Yeah. So SRAM is basically volatile. So you're reading the data for 0 days, 7 days, 33 days, and 50 days. So do you rewrite the Einstein image, or you just don't the SRAM for the complete 50 days?
No, you don't rewrite the image. Basically, this image is burned into the POF data that exists on the chip.
It's power up state.
The power up state, the basic power up state has now been changed to this Einstein image.
Okay, so Okay, so you mean the Einstein image has been stored in the power up state?
Sorry?
The Einstein image has been stored inside the power up state of SRAM.
Yes.
Okay, that makes sense. All right, thank you.
Yes.
So, one of your memories where the number of distance was going down after the radiation.
Yes.
So you had your powered up state completely shifts kind of the effect of the radiation on its stem.
This is the slide we're talking about, right?
No, where I think that one. Yeah.
This one?
The next. Yes, yes.
Okay.
And so you saw that your ISSI grams in the ISSI ramps when you are storing the inverted part, right?
Correct.
So distance is actually
Decreasing, yes.
decreasing.
So you're writing the puff onto you're imprinting the puff onto the memory location.
So the inherent path is actually flipping.
Yes, it's
It's
changing.
actually flipping.
It's becoming the so storing your because initially what was a 0, you're holding a 1, and it causes a 0 to burn in. Yes.
It got recovered after a few days of.
Yeah, they all start annealing towards whatever they were before radiation. Not exactly back to the original state, but after several months, they say 50% of it is annealed, approximately. So that's what this was, right?
Yeah.
This annealing. This applies to everything. It applies to both SRAM, MRAM, SRAM, flash. In all the experiments, once there's TI defects, if you let it anneal, it's going to revert back to its original state. Not exactly, but it starts moving in that direction.
But it never goes back to its
No.
pure state.
Yes.
Do you vary power and voltages at all of the chips? Do you change any of those settings?
No, these are all operating at nominal voltage, which is 3.3 volts of the chips. Essentially, the higher the operating voltage, the greater the radiation limits.
You maybe talk about what's the sample size of the chips that you tested with?
These are 4 chips.
4 chips?
Yes. Anyone else have any questions online or Zoom folk, Anik, Nisha? Any questions?